All right, today we are diving into a really cool family of elements, ones that are absolutely fundamental to our world. They connect the very air we breathe to the tech we have in our hands. We are talking about the chalcogens.
So think about this for a second. It kind of sounds like a riddle, right? The gas that fills our lungs and keeps us alive, and the raw materials that literally build modern life, what's the link? The connection might not be obvious at first, but trust me, it's a huge one.
And boom, there's our answer. It's the chalcogens. The name itself is a dead giveaway. It literally means ore forming. And that's because most of the metal ores we dig up out of the Earth's crust are found as oxides or sulfides, which are just compounds made with these very elements.
Okay, so let's get properly introduced to these ore formers. Who are the members of this super important elemental family?
Here they are. You've got oxygen, of course, sulfur, selenium, which is super important for stuff like photocopiers. Then there's tellurium, and the radioactive one, polonium. Now, what really ties them all together, chemically speaking, is their structure. See, they all have 6 electrons in their outermost shell. That means they're all just 2 electrons away from being perfectly stable, and that shared feature basically dictates how they're going to react with everything else.
But what's absolutely staggering is how one member of this family just completely dominates. Oxygen makes up almost half of the Earth's crust by weight. I mean, look at that chart. Sulfur is a super distant second, and the rest are barely even there. This incredible abundance is exactly why our planet is so rich in oxides, from the rocks under our feet to the water in our oceans.
You know, being the first in any family often means you're a little bit different, right? And in the world of elements, that is definitely true for oxygen. It does stuff that chemists call anomalous behavior.
And this slide just shows you how different oxygen really is. While all its siblings are solids at room temperature, oxygen is a gas, just floating around as these simple 2-atom molecules. But its most important, unique trait? Its ability to form these super powerful hydrogen bonds. That's the very property that gives water all of its incredible life-sustaining qualities.
But oxygen's story doesn't just stop with the O2 we all breathe. Like a lot of elements, it's got this kind of shape-shifting ability. So what other forms can it actually take? Well, it can exist as different allotropes. The 2 big ones are dioxygen, that's O2, and ozone, O3. It's the same element, just a different arrangement of the atoms, and that leads to wildly different properties. One we need to live, and the other protects us from UV radiation way up in the atmosphere.
Making ozone in a lab is a pretty energetic process. First, you have to zap regular O2 with a powerful electrical discharge. Think of it like a tiny lightning strike. This blast splits the O2 molecules into individual, really reactive oxygen atoms. Then, these lonely atoms quickly latch on to other O2 molecules, and that's how you get O3, ozone.
Now, if you think oxygen having 2 forms is interesting, just wait till you meet the next member of the family. Sulfur is a true master of allotropes. It's got a whole collection of different faces.
So at your standard everyday temperature and pressure, the form of sulfur you're going to find is this one, rhombic sulfur. This is its most stable, most comfortable state. Rhombic sulfur has that classic bright yellow color, and it's built from these really beautiful crown-shaped molecules made of 8 sulfur atoms all linked up. You'll also notice it doesn't dissolve in water at all, kind of like oil.
But that stability only lasts for so long. Like a lot of things, sulfur changes when things get a little heated. So, what happens when we raise the temperature?
Once you heat it past 96 degrees Celsius, it goes through a transformation. The rhombic form actually rearranges itself into a brand new crystal structure called monoclinic sulfur.
Now, this form is only stable inside a pretty narrow temperature window. And instead of those blocky crystals, monoclinic sulfur grows into these long, delicate, needle-like prisms. But what's really fascinating is that it's still made of the exact same S8 crown-shaped molecules. The only thing that's changed is how those crowns are stacked together.
This ability to change form is pretty neat, but it's sulfur's reactivity that makes it a true industrial giant. It is the key ingredient in producing the undisputed king of chemicals, sulphuric acid.
And the method that's used to make it on a massive scale is known as the contact process. This is honestly one of the most important chemical processes in the entire world, responsible for churning out millions of tons of this acid every single year.
The whole thing really boils down to 3 key stages. You can think of it as just adding oxygen to sulfur, but in very carefully controlled steps. First, we make sulfur dioxide.
Then, we add even more oxygen to get sulfur trioxide, and finally, we'll safely turn that into our final product, sulfuric acid. The first step is just beautifully simple. You literally just take elemental sulfur and burn it in the air. The sulfur combines with oxygen and it produces sulfur dioxide gas, SO2. Easy enough.
Okay, step 2 is the absolute heart of the contact process. This is where we oxidize the sulfur dioxide again to make sulfur trioxide, SO3. But this reaction is slow and it's reversible. To make it actually work efficiently on an industrial scale, you need a catalyst, a little helper, in this case vanadium pentoxide, to speed the whole thing up.
So for the final step, you might think, why not just add water to the sulfur trioxide? Well, don't. That reaction is dangerously explosive. So instead, the SO3 is dissolved in concentrated sulfuric acid that's already been made. This creates a substance called oleum, which can then be safely diluted with water to produce even more high-purity sulfuric acid.
And the result of this whole carefully controlled process is incredibly pure sulfuric acid. The efficiency of the contact process gives us a product that is over 96% pure. And this high grade is exactly what's needed for everything from making fertilizers to powering the batteries in our cars.
So we've seen how this one family of elements connects the air we breathe to the acid that builds our entire modern world. It really makes you wonder, right? What other hidden connections, what other essential processes, from the biology inside us to the geology beneath us, are being quietly powered by these remarkable ore formers?